Good day, ladies and gentlemen, and welcome to the Quality Cyberseminar conference call. My name is Betsy, and I'll be your coordinator for today. At this time, all participants are in listen-only mode. You will be facilitating a question-and-answer session towards the end of this conference. If at any time during the call you require assistance, please press star followed by 0, and the coordinator will be happy to assist you. I will now turn the presentation over to your host for today's call, Mr. Dr. David Crisell. Please proceed, sir.
Thank you. Good afternoon, and welcome to the second cyber seminar of the spring 2008 series. So my name is David Crisell. I'm the Quality Program Manager, and just before a couple of items before we get started, one is if you have technical problems, please you can send a chat message to host, and I will see it, and I think folks at WebEx will see it as well. And also, we'd appreciate any general comments, criticisms, feedback, etc. can be sent to commanager@quality.org. Also, today's presentation will be recorded and available for download next week at quality.org/stemcurrent.html on the Quality website, so you can review this, replay it, use it for your classes, etc. Before we get started, I just want to make a few announcements, quality announcements. Remind you that we still have 2 more talks in this series for the spring. We have Jim Smith on March 14th, who will be speaking on flooding in the urban environment. And on April 25th, we've got Witold Krajewski, who will be talking about Hydronexrad, community resources for use of radar rainfall data. Also, some other interesting items from quasi-related is that we will be having a biennial, or our inaugural biennial science meeting July 14th to 16th in Boulder, Colorado. The theme of this year's meeting will be resistance and vulnerability of natural and man-made systems. And we are fortunate enough to have Wilfried Precip from Cornell University, who will be giving the inaugural Pete Eagleson lecture on hydrologic science. And we will also be having Dr. Robert Hirsch from USGS, who will be giving the Red Volman's lecture on humans and water. Additionally, for the graduate students out there and those of you who have graduate students, I'd like to remind you that we have the Hydrographics competition, which is a competition for visualization, short films, and animations related to hydrology. More information about that is available at quality.org/hydrographics. Today's talk will be by Dr. Upmanu Lall. He's the inaugural Alan and Carol Silberman Professor of Engineering at Columbia University and Senior Research Scientist at the International Institute for Climate Prediction. Today's presentation will be on what does a hydrologist need to know and do about climate change adaptation. Manu, give me a second, and it shall be all yours. You should have Manu, you should now have control of the meeting.
Here we go. Okay. Thanks a lot, David, and welcome to all of you who are kind enough to come to this talk. I had a little bit of a computer disaster, so as a result, this talk is not quite the talk it was yesterday. It's a different talk, which was abstracted from materials that were more readily accepted. But let me start off and point out what I'm trying to do in this particular talk first, and then we'll go to the talk itself. As you can see from the title, this starts from the idea that we probably need to start adapting to projected climate changes. At least this is the buzz that many people are putting out today. So the focus of this talk is not about climate change science per se. It's not about the hydrologic modeling or hydrologic science needed to connect to climate change, but to get closer to the question of how one could work towards adaptation-related issues, and what's the field of play perhaps for hydrologists. That was the original intention of the talk, and I had drawn out some arguments in that line. Specifically, the way we'll go about it is that we'll review some of the information that's available today with regard to the skill and the ability of models that could develop scenarios for us, and then we look at some examples of ideas on how some aspects of adaptation, not comprehensive, can take place. And then in the end, I'll try to open things up for discussion by talking about where I think things can go from a hydrological perspective in this arena. See if this works. There we go. Okay. So the basic idea of adapting to climate change fits that of adapting to a changing environment, and some of the elements from a hydrologist perspective or a water resource manager's perspective, since this talk ended up going more in that direction than hydrology more broadly, relate to the items that I've got on this slide. And they are first of course changing climate, because if you pay attention to any of the things people are saying about the change in climate, the thing you start realizing, if you think about it at all, is that most of the significant impacts broadly based, particularly away from coastal areas, are related to agriculture, human health, ecology, and society, and all these come through water. So if you take projections of future climate encapsulated as atmospheric state variables, they have to go through the hydrological chain before you can figure out what the impacts are going to be. And that's the key step in trying to understand adaptation. So in the water resources context, what this translates into is that typically people are talking about increased variability manifest as increased frequency of floods in some places, increased frequency of droughts in other places, and increased frequency of both of those in yet other places. In many of the areas that are today water stressed, namely in the tropical belt around the world, there's indications that aridity will increase as per these models, and that becomes a concern. For example, in the Middle East, in Israel, Palestine, and that region, many of the models predict that the mean annual rainfall will tend towards zero in the by the end of the century. From a hydrological perspective or a water resources management perspective, though, many people have argued that changing population and water use demographics is perhaps a more important stressor than just changing climate. Through increases in water demands for agriculture, and as I indicate, for example, in India and Bangladesh, places like that, we've gone from 1 crop per year of grains to 3 to 4 crops per year, and clearly these things use large quantities of water. 90 to 95% of water usage in those environments comes from this form of agriculture. There's also increasing competition as new demands of the sort that I've got listed there emerge, and they have water quality, quantity, and ecological impacts. So the issue of adaptation has to look at the combined effect of all of these things. In some cases, this maps into a significant need for new infrastructure to manage fluctuations. In many cases, this translates into a situation where in the long run, we probably are going to see a high degree of migration from tropical zones to high latitude zones as Canada, Siberia, and those sort of places become much more habitable, both in terms of water and temperature. These people talk about the combined effect of these leading to the potential for major ecosystem and health issues, and how one could deal with those. And what this combined set of things translates into is a recognition that we have many, many things that compete for water usage in watersheds, and we'll have to get much more flexible and much more efficient in terms of how we do these things. So this is sort of the scenario of adaptation that we can see from a water manager's perspective if you buy into the changing environment story, which is very difficult at this point not to buy into. Specifically now, what do we need to be able to do to go in this direction? And this is a fairly standard sort of thinking on this problem. First is the issue of how do we develop scenarios for the future. And since this particular talk hits the climate change issue more than the demographic change issue, I'm going to stay mostly with that story rather than the overall changing environment story. The issue that comes up, first of all, is that if you look at general circulation model-based regional water supply demand forecast, this is precipitation, this is evaporation, this is soil moisture, this is runoff, this is humidity in the region. The closer you get to the hydrologic cycle, the higher is typically the uncertainty at the regional scales which are important for adaptation. And if we talk about adaptation, one of the possibilities for adaptation is walking up a staircase instead of falling off a cliff, or walking down a staircase in that particular metaphor. So the idea is that if you could start anticipating what's coming up in the next year, next season, next few years, then you'll be able to do this better. And since there's a high uncertainty in the longer term predictions, the question is, can we do these sort of forecasts in arbitrary locations better than what we've been able to do in the past, and how we can use them? This translates into two challenges for water resource managers. One is you want to be able to demonstrate that you have predictive ability in the short term. The second is you have to be able to show that with the range of climate variations in supply and demand that we can experience, that the rule that you're proposing for adaptive management with forecast will actually work in a robust way over a long enough time period, that it doesn't open up new risks. And to be able to do that, we have to understand what has happened in the past, what's the range of fluctuation, and can we at least adapt to that better than we have done with the fixed sort of rules that we have today. One interesting caveat with this story is that we currently do not incorporate the adaptive rules, and if we start developing and testing these, we have to see whether or not there is a willingness on the part of people who are water managers to do this. Some people have written that in the United States, this is not going to happen very easily, particularly with seasonal to interannual forecasts. I disagree with that, but the first bullet that I have under that particular red bullet goes to the idea that if we start looking at climate change scenarios, the areas which have high climate sensitivities and also high water stress, namely the tropics, have also seen long periods of significant climate shift in the last 400 to 700 years. So if you look at the Sahel, if you look at the Indian subcontinent, if you look at parts of China, or look at Northeast Brazil, for example, these are places where people are going to have a much stronger incentive to do something than in perhaps the mid-latitudes that we're talking about. The next question is, suppose you were able to generate these scenarios both on the supply side and on the demand side, what do you use them for? And some of the ideas people have are, you would have to time investments in new infrastructure to meet demands before they become critical. This is exactly something that has been going on in the U.S. already without worrying about climate change. An example of that is Tampa Bay, which was mandated to reduce groundwater usage for environmental reasons on a schedule, so they have to come up with investment timing strategies for coming up with supply sources that meet their demand projections. So from an engineering point of view, this is nothing new to us. The new thing here is that we are being asked to develop these in an environment that is much more uncertain than perhaps what we've gotten used to in terms of planning and the second item that people talk about is new rules for water allocation and facility management that are responsive to changing climate and changing environment more broadly. So these are some of the examples that I'll take later in my talk. Similarly, people are arguing that maybe you can't really deal with all the exigencies that climate puts on you, particularly with extremes, and we need to be much more aggressive about soft solutions, which are insurance and financial risk management issues. Given the length of the talk, we've been working in this area, but I'll just hit on this briefly. And finally, comes the question of how do you apply adaptive rules that you have developed which use forecasts, and how do you actuate emergency plans, response, disaster relief, disbursement. And again, I'll basically just be hinting at those today instead of developing those more fully. Technically, this can be all boiled down into this slide that I have here, which is how do you develop scenarios all the way through this hydrologic system? How do you develop credible near-term forecasts? The difference in scenarios and forecasts here is that the lingo that people are adopting is forecasts are typically probabilistic forecasts of something in the near term, and scenarios are long-term scenarios akin to what we have done as stochastic simulations in the past, but in a changing environment. And then how do you develop and design these models for all the diverse sort of uses that are indicated in the flowchart right below there. Okay, so I'm going to move on from there. And this next segment is to address what are we able to say about hydrologically interesting things from a climate change adaptation perspective. If you are a climate person or if you're a hydrologist evaluating the stories that climate people are putting before us. So I started working in this area roughly around 1987, and I dug back through the stack of papers that I had from that time and chose two essentially at random from the stack I kept as things that were good. And these are a couple of stories there, both from David Ryan, because he was the section of the folder that I landed randomly on. And it's interesting what people were saying in those days. And the first story is the idea that water vapor increases as temperature increases, forced by CO2, and then you have a stronger greenhouse feedback from that, and you could possibly have a runaway greenhouse. David Ryan actually published some papers in JGR roughly around that time showing scenarios where the world was roughly cooked by 2010, and now we are at 2010, so the runaway greenhouse didn't quite happen. And the second one is the highlighted stuff in red, which is there are a lot of models being used to evaluate hydrological effects of increasing CO2, but the consistency across these models is not there. So that was the state of play 20 years ago, which was basically we didn't really know what was going on very well. So what's happened since then is that there's been a lot of very intensive research, and a lot of very bright people have worked in this area. And the models have improved in resolution, they have improved in process parameterization, and they have improved to the extent that many of them do vaguely credible forecasts of the near term and are able to reproduce climatology of various things at different levels. So what we'll do is we'll go back to the climate change adaptation perspective, which is somebody who's a water manager sitting there in Missouri, of course, and saying, please show me what you really have, and how does it relate to things that I may be interested in. So let's walk through a bit of that, and it's going to be somewhat negative. So at the very beginning, I'll say that this is not my view of climate science and hydrologic science coupled to climate science in general. This starts from a very specific exploration one individual started with who wanted to do this. So I'm going to sketch that out. And that individual is, okay, let's do this little experiment. Okay, that individual is right here, Francisco Assis Souza Filho, who was a water manager in the state of Ceará in northeast Brazil and came to work with us on this problem. So on this particular slide, what I have are predictions of changes in precipitation in northeast Brazil over from 46 different runs. Some of them are the same model and different ensemble runs from it, changing initial conditions, and some of them are, single runs from different models. So this covers the broad spectrum of most of the models that are out there, and what has been run here is the IPCC scenario A1B, which assumes that in the future we'll have a balance across all sources of energy production. So there's a fair amount of renewables that come in this particular scenario. And what you are looking at is a change in precipitation from 20th century divided by the average 20th century precipitation. So it's the percent change, or the fractional, it's the fractional change in that area. So what you see is a large variety in the results from these models, something that's happy to predict 5 times the Precip that we saw in the 20th century in this location, and most of the others that are showing a decrease in Precip. So our thesis thing was maybe I need to do downscaling of these GCMs and maybe I'll have better results there, and I was concerned about that particular statement because when you have that higher variability and people consider this to be uncertainty, maybe in this region you could gain by doing regional climate models and downscaling, maybe not. Now, the one comment to give here is that if you look at seasonal forecasts of all the places in the world, this is the region that in climate models and in statistical models has one of the highest seasonal prediction skills. So you would expect things to work well here if we assume that we are running the same models on out for the global climate change scenarios. And at this point, many of these models run for seasonal forecasts and for climate change scenarios are pretty close, but in many cases they are not really the same. The physics parameterizations are somewhat different, and the CO2 forcing obviously is not there in this. So that's the story to start out with. So then Assis, this is, the axes are zapped, but let me tell you what this plot is. So he looks at can you reproduce the climatology of rainfall? So on the x-axis here, we should be running from calendar month 1 to calendar month 12. And on the y-axis here, it's the percentage of annual rainfall that occurs in that month. And the red curve represents the fraction of monthly rainfall relative to annual rainfall from observations over the 20th century. And then each of the gray curves is the climatology over the 20th century also, with CO2 varying as prescribed by 20th century observed CO2 variations for the same location. And what you see here is dramatic. I mean, there's a lot of uncertainty or variation, but there are also models that are just completely wrong. Now, it just so happened that this set of models happened to be the first ones that Assis pulled for downscaling, and he was stunned by the fact that the models put the rainfall in completely the wrong season. So much for the physics. He was a bit more reassured once he got the others in, but you can see that even at this level, we are starting to see a significant problem. Then he looks at long-term variability. So now on the x-axis, we have the period in years associated with interannual and longer-term variability. The data that went into this is annual rainfall from the 20th century in the same region. And the red curve is what you get as the spectrum associated with the 20th century data for Northeast Brazil. The gray curves here are percentiles of the spectra associated with each of the 46 runs that we had. And if you look at the median, which is right here, you basically see that there is no low frequency variability in these models in the sense of what you see from the data. So if you're a hydrologist, you say, give me climatology that is right, at least, if I'm going to make agricultural decisions, and give me long-term variability because I'm interested in the structure associated with droughts, because I have reservoirs that have, say, 3 to 5 years worth of mean annual flow storage, and I would like to know when that particular setup is at risk. So we are not getting that here. So we moved back, and I said, look, forget about this. The people who are working on these models write that as you start increasing the scale because of the resolution of the GCMs, by the way, that's about 12 grid cells in a GCM averaged over in the stuff that you were looking at before. It's not 1 point or 1 grid cell. So what they talk about is that as you increase scale, you get more reliable predictions, and then you need to run a downscaling model and so forth. So my reaction was that why don't we go to the global scale and see what we learn? Because if these models aren't working there, there's no point wasting our time with them. So here what we have is data put out by a group in England, Mike Hume and Jones, who've made gridded rainfall data for the whole world using 1900 to 1998 for precipitation and temperature. So this is not from models, this is simply from data. So we are trying to see how does rainfall change with temperature, because one of the issues that has come up is in a warming world, we'll have an intensified hydrologic cycle, so rainfall should increase with temperature overall. So what we see here is 10-year moving averages of precipitation plotted against 10-year moving averages of temperature as you walk through from the beginning of the 20th century to the end. And what you see is that initially as temperature increases, we are sort of seeing increases in precipitation, but in the latter half of the century, we are actually decreasing precipitation as we increase temperature. This is sort of odd, and we don't know whether this is an artifact of the poor grading of this data, lack of representation, or what goes on. So we explored this some more, and here is what you get from the NCEP reanalysis. The way this is done is that there's radiofront data and all various other data sources available globally, and then there's a climate model run on a daily time step, ingesting that data every single day. And so this is really an interpolation of the data by that model, and precipitation generated by that model, and temperature at the surface generated by that model. This doesn't go back all the way. This is from 49 to 2006. So what this shows us is that we basically ended up, during that period, cooling in the beginning a little bit, and the rainfall decreases along with that, and then the rainfall increases. So this fits with our physical notion of what should happen. This is land and ocean data. What we were looking at with the observations is land only. So now let's go and see if we superpose land only from the reanalysis, dropping the ocean data and the observations just for this period. And what you see is that over land, the reanalysis data set, which is the purple, is qualitatively exhibiting the same behavior, but there is an offset of where these values should be. So there's a systematic bias in the mean values, but the tendencies are relatively similar, suggesting that perhaps there's a dramatic increase in rainfall over the oceans, which is interesting in itself, but not over land. So then we decided that maybe we ought to look at, there are two different reanalyses available, one by the European group at ECMWF, which is the red stuff, and the NSEB, which is an American reanalysis product. And what you discover is that these two guys don't agree with each other at all over land over the same time period that they've been run. There are significant differences in behavior. Now, notice that what most people do is they look at either precipitation fidelity or they look at temperature fidelity. They don't look at the state space or the phase space associated with these things together. And that's when these differences pop out much more dramatically than if you compare each individual thing. Remember that at the global scale, once you average at that scale, the magnitudes of these numbers in their trends is relatively small. So that suggests that we really do have some work to be done on understanding what is really going on with the global hydrological cycle under CO2 forcing. Finally, we decided that maybe we should look also at the data that is more reliable over land, just going from 60 north to 60 south, excluding the polar regions in the Hume-Jones graded data set. So we did that, and if you look at that now, what is happening is that the trend for reducing precipitation as temperature increases in the latter half of the century is more pronounced. This is now remarkable because this is actually contrary to what we are getting from most of the GCMs and most of the assumptions people have about the way the climate system should behave. It's consistent in one aspect, which is that we expect precipitation to increase in the polar region. So having subtracted the polar regions out, we are seeing a more dramatic impact in this region. Now the fact is that if you're interested in climate change adaptation, you're much more interested in land. So even if the polar regions were seeing increased precip and the ocean was seeing increased precip, the signal that we are getting from this is one of considerable concern, just in terms of believing this trend and believing the fact that NSEB exhibits a similar trend. So here's now those 46 runs that we were looking at, trying to see how these people were responding to CO2 in the precipitation temperature change coordinates in the 20th century, not looking at the 21st century, just looking back to see what happened with them. So this cluster right here is all the departure from the 20th century mean, fractional departure from the 20th century mean in the first 30 years of the 20th century. So those are the CO2 conditions associated with these model runs. And then this stuff in the brown box is what comes at the last 30 years, 1970 through 2000 in these models. So the first thing you see is that these, in the precipitation temperature coordinates, in the model runs, these two groupings are clearly separated. So that's good because at least we are seeing that in the models there's a response in terms of both precipitation and temperature that is separable as a forcing to CO2. But what you see is that some of these models have a very dramatic increase in precipitation and temperature. Others actually go in exactly the opposite direction. Essentially, they're all over the place in the tendency that they suggest would come in the precipitation temperature coordinates even over the 20th century, which is the period over which much so-called pseudo-calibration has gone on with these models, in the sense that to match the temperature record, people have gone to great lengths to bring in solar forcing, to bring in volcanic forcing, to bring in all the forcings that people think were reasonable to match the temperature record. But in the process, if you look at what happens in the precipitation and temperature coordinates, we still don't have a clear-cut story even for the 20th century. Okay, so now that I have made myself and you perhaps quite depressed about the possibility of using these things as scenarios for climate change adaptation applications in hydrology. Let's show you what people are doing. One example from our group of the kind of things that can be done. And the idea here is that the scale at which the GCM does computations is typically 1 degree by 1 degree latitude longitude to 2.5 by 2.5, depending on which one you're looking at. And if you're doing adaptation, you want data at the scale of a watershed, and how do you get that? So what is typically done is that from the GCM, a regional climate model is run. And what some people do is that then they will take the output from that and start feeding it into hydrologic models. And then you realize that the precipitation coming from these models usually has very significant biases relative to what you're looking at historically, so you need some way to correct it. So people will do regression or various other things to correct that, and then they happily use it. And many of the people who do this talk about this being the physics-based approach. And I find that to be a little odd, considering that many times these corrections are factors, multipliers of 2 or 3 on precipitation. So if your physics is sort of working, why do you need that bigger correction, or what did you get wrong to do that? But nevertheless, people do that. And one of the main thing we have learned from the work we have done in this area is that it is the precipitation from these models that's problematic. The circulation patterns often are very good. So what people do then is that they go back and compute some indices of key circulation, atmospheric circulation parameters, either at the regional scale or at a larger scale, and then use those to drive statistical models, which then generate stochastic sort of simulations of what goes on. In our case, what we have done here is that we've moved from what people have been using in the past, which is non-homogeneous hidden Markov models and models of that genre, to hierarchical Bayesian models, with the idea that we would directly like to predict station statistics of rainfall that people might be interested in. For example, seasonal rainfall totals, the transition probability for going from a dry day to a dry day, wet day to a wet day, the probability of getting a 7-day dry spell, the length of the maximum dry spell, and the total number of dry days in the season. So instead of generating Markov chain style simulations, establish these statistics from the historical data and then use the climate model output to directly estimate these, simultaneously maintaining correspondence across those. So these models are one way that you can get something useful out of it. You should still be nervous using them in the future because you are clearly extrapolating, but then keep in mind that anything that is being done here is an extrapolation, and the argument that's being made here is that maybe the climate models are able to get circulation right given their physics. So if you have a mapping from that circulation to the hydrostatistics, that mapping doesn't change in the future, and that assumption is false because we know that the atmospheric moisture content will change, but still this is the crutch that we are working off of. So in this particular application, at least on my slide, I'm not able to see the box plot, so it's hard to see what's going on. This is for Israel, Palestine, and there are 4 boxes in each slide for these statistics from observations from this entire chain of models for 1961 through 1990 to show that our model is working reasonably well in representing the mean and the variability of each of these seasonal statistics. And then from the model projections for 2071 to 2100 for a business as usual scenario and for the IPCC preferred scenario for mitigating climate change. And since people can't see this very well, I'll simply say that what we learned from this was that unlike the direct runs from the models, which were basically drying out this area completely, what we see is that in the amounts we get much greater variability, but not a statistically significant change in the mean rainfall in the region. These box plots and so on are taken over all 19 stations and over all years, all days in all seasons of all years over that time period. But we get a dramatic increase in the dry to dry day probability and the wet to wet day probability and in the dry spell statistics. So what we start seeing is that really what the change that is being projected in the future by these models is persistence in the regimes that bring moisture to these locations, dry and wet, and that accounts for the increased variability in the amounts also. That's a very different adaptation metric than what you get directly from looking at the models. So the main point I want to make with this set of stories is now the following. There are significant biases at every step of this modeling chain, going from climate to adaptation, and we still don't have the physics right, despite much progress. And in places in the tropics where the water conditions are already highly stressed, it's not reasonable to say what we've been saying for a long time, that you're going to keep building this model chain, and when the climate models improve, we'll have the whole thing working. I think on the science side, we have to keep doing that, but on the adaptation side, it's a case where we have to start doing some things and not wait. And the second big point that I want to make here is that if you are used to operating in the model that the Harvard Water Program put together and everybody more or less follows in various flavors today, which is let's do risk-based analysis and come up with things that are legally defensible in terms of meeting target levels of risk and reliability, those people will want you to demonstrate that you are not making things worse on those metrics. That means that you have to have the probabilities characterized and verified to a certain extent. This implies that there has to be a proper application of a statistical methodology at the right step. The question is, what is the right step? Do you correct the GCM rainfall, then you GCM rainfall, feed it into a hydrologic model, correct the biases in the hydrologic model, or do you run through this chain and directly try to finally build a statistical model that gets things right? This is an open question. This is still leaving open the question of whether whatever we are trying to do following this process will really work. And the main message I want to leave you with here is that I think from an adaptation perspective, we are going to have to take a what-if approach as much as we are going to take a very hard quantitative approach on it. You're going to have to think about these things a little bit more. And that's the point I would like to develop and reinforce further with this analysis of change and variability. So if we recognize the way the climate system works, we have long period variations in climate. We have abrupt changes also, and many people are familiar with these ideas. So, whoops, this thing is basically dead. It's popping up. So we have ENSO, 3 to 7 year structure variability, many hydrologic impacts. There are people who talk about many other things, for example, the Atlantic multi-decadal oscillation. So the main idea is there will be long regimes that you have to plan for, and how do you do that? This is India. I'm just going to move on. One point I want to make with that is that people are used to these cycles, but the question is, what is the nature of these cycles really? And this is a model run which was a numerical integration of tropical climate, ocean atmosphere model, Nino 3, for 110,000 years with stationary climate. No CO2, no orbital variations, nothing like that. And what's computed here is the time series of the Nino 3 index, which represents El Nino variability. And that's out here, and this is a 1,000-year snapshot randomly drawn from that 110,000-year integration. And what you see is remarkable. Most people talk of this as a 3 to 7 year variation. This is represented here with a wavelet spectrum. And what you see is that actually there are century scale variations and longer variations that show up here. So the nature of the climate system is that you have pronounced structure over long periods of time, and this happens naturally, it doesn't require forcing. So in terms of climate change adaptation, we need to actually understand this, because if we can't even come up with plans to understand this part, the stuff that we are speculating on in the future is going to be very difficult. I'm looking at the clock and realizing what's going on, so I'm going to start skipping through some of these things, and you can look at them later yourself. There's also abrupt changes that happen in the climate system, and a lot of people are concerned about these now in the context of thermohaline circulation in the Atlantic and what that could bring. The big story here is that you could have a dramatic reversal. There are no models that predict these kind of things accurately or have the necessary physics to do so. So this is mostly to reinforce the idea that we have to be using our brains as much as quantitative models here. So let's skip through this. This paper I would recommend to you to look at. The person points out various ways by which abrupt climate change could occur and the possible timescales over which those changes could occur and what their possible impacts are. It's a comprehensive summary of that sort of a thing. Okay. So I'll skip through to some examples now, and the idea here is how do we move towards adaptation, recognizing that there is considerable variability, and one of the things that has been talked about lately has been the 7-year drought in the Colorado and what its implications are for water supply in that region. So let's take that. This is a headline from last week's New York Times, and refers to a paper by Barnett and Pierce that got accepted in Water Resources Research, and then this group has published various other things. They essentially say that by 2017, there's a 50% chance that Lake Mead will dry up, and this is based on an assumption of 10 to 20 to 30% reduction in mean rainfall and mean annual flow based on climate model predictions generally over this area. I would like to put that in a different context. Here is the 20th century record of Lee's Ferry, which is the gauge that's used as a benchmark for this analysis, and that's where we sit in the current period, and that's why people are concerned, because this is the drought of record as far as the 20th century is concerned. Most of you probably know, but in case you don't, this is the period in which the water allocation to the different states was done, at least the record on which it was based. That's been wetter than the average flow over the 20th century, so we already sort of got it wrong in the climate context that we allocated too much water based on this short record. The key thing to point out here is there are long-term fluctuations that go on, and we need to understand those long-term fluctuations, or if we can't characterize them or understand them, we have to have a strategy by which we understand regime shifts and how we are going to operate with changing allocations over those time periods rather than the fixed allocations that were based on one period. So if we look here, this is from Eric Kuhn, who's a Colorado water manager, and he characterizes the situation as follows. The first part of the century was a period with high mean flows and low variability. The second is low mean flows, increased variability, and the last period is high and low flows and high variability. His argument is that the period of development of population and growth has happened sort of like that. The reservoirs went in roughly around here, and it took a long time to fill them. So really, the same sort of drought may have happened earlier, but it wouldn't have been nearly as much of a crisis as it is today. And he wants to know what comes next. Is it this sort of a behavior, this sort of a behavior, or this? So if you look at the paleo record, and this is a reconstruction by Dave, Nico, Connie Woodhouse, and others using 3 rings, what you suddenly realize is this is the drought of record. But if you look back 500 years from their reconstruction, and these things are fuzzy here because this is a statistical reconstruction and they've put confidence limits on those. There are 7 such droughts in the last 500 years. So that doesn't make the current situation look nearly that dramatic. And if you look at the overall trajectory here, it doesn't look like a whole lot has really changed. This is stationary, but with long-term variability marking the flow, and also abrupt changes in at various times that go on. Now, there's a paper by the Scripps group, Barnett and so on, who argue that the changes that you see here are significantly due to CO2, so keep that in mind also. The question is, how should these long periods be managed? And here, I'm trying to show you what happens in terms of failure statistics. So keep in mind that Barnett and company argue that there's a 50% chance that the reservoir dries up by 2017. And those who work in water management will recognize that anytime you design a dam storage with a particular set of demands with critical period hydrology, you are actually designing it to go empty once in the driest period in that hydrology. So there will always be a time point or a reservoir storage elevation level at which there will be a 50% probability for some point in the future that it will go exactly dry. So that doesn't have much to do with climate. Of course, if you reduce the mean inflows into it, as these people did, you will go dry quicker. So what's done here is that we ran through the allocation flows through the Lake Powell area and calculated what would be the variance of the amount of failure we would have as a function of period. So this is not 1,000 years, this is 1, 5, 10, 20, 30, and this scale here should be 200. So this is done with the 3-ring reconstruction of 500 years, running through the site, allocating the water, and these are, so what you see basically is this is really around 80 years. With an 80-year periodicity, we expect to get dramatic failures in supply if you allocate that water, if the dam were not there. If you put the dam in, then the picture becomes this. And I'll just jog this back and forth, and what you see is that what the effect of the dam is exactly what you expect, which is that at the lower return periods, the dam is effective and is able to take care of the failures. But at the longer return periods, the dam basically makes no difference. Whoops. Okay. So the idea is that even though we have built these things in the past, and in this case for 5 years of mean annual flow, we were always exposed to long-term climate variability, and regardless of climate change, we need an adaptation strategy for how we are going to allocate water and meet those failures. Okay, so that's basically the lesson that this thing is trying to tell you, which is missing. Oh, here we go. Okay, so the idea is that storage projects can reduce these risks but have limited impacts on these persistent departures whose time scale is greater than that implied by the storage capacity, and we really have to start looking at soft technologies for adaptation. How do you shift, how do you anticipate what might happen, how do you shift water use to critical needs from low value needs, and how do you compensate the people who are then affected in that particular way? So that's one possible adaptation strategy that one goes towards. What we can do today, given the methods that we have available, is identify how these things work in space and time using a combination of data sets and monitoring, and then try to identify as quickly as possible that we have undergone a shift in the type of climate regime that we are working with, and then start invoking the adaptive rule that is appropriate for that particular scheme. So that's a possibility. We have done quite a bit of work along these lines in different places. So this is basically advertising that work in Brazil, and this is published now, so I can skip through this. But the basic idea is that you take forecasts and for a season ahead and apply them to different applications where people can adapt their water uses for them. And to facilitate those, this is the example of the quality of these forecasts that we get in a blind mode, which is really quite good. Can't do that everywhere. But the idea is that in a participatory decision process, instead of having fixed allocations like is the case in the Colorado today, you get the forecast and you develop an allocation plan where people propose what they would like to have, and there's a negotiation process by which contracts are given out at specified reliability and price. And then if you aren't able to because conditions are worse, then there are compensation procedures in place. So this is an idea for how adaptation could take place. The other area where people are interested now is the natural hazards area, and this is from a paper by Chris Milley and others who pointed out that in many parts of the world, under these climate model-based scenarios strictly, you would take the 100-year flood and it might become a 2 to 5 or 5 to 10-year flood, which sounds pretty dramatic. And this paper came out soon after the flooding in 2002 in Europe, and people were starting to talk about how climate change is the issue, and then these papers came out saying, no, in the paleo data, we had periods which were more floody than what you are seeing today. The basic idea is that how do we want to start understanding these, given that, and applying these in terms of risk management, given that we don't really have hard abilities to, in my view, go from direct integrations of numerical models to flood predictions in a adaptation sort of context. So if we consider that, whoops, no further movement. I guess this is telling me I have to wind up my talk. Okay, this is not moving at all.
Do you want me to take it over?
Yep.
Okay. Are you there?
Yep, I'm there.
Do you see the slide?
No, my screen is not moving.
Okay, I've got slide 44 with your maps of the North Pacific.
Okay, let me launch something here so that I can keep up with you.
Actually, the count's going to be off because I added some slides to the beginning.
44, so, okay, well, if you have the maps of the North Pacific, let's go there. Okay, so the thing that we've been working on for the last 7 or 8 years is trying to understand how flood processes relate to climate. And the interesting thing here is floods are inherently a short-lived or high-frequency phenomena. It's a weather phenomena. And climate, by its definition, is a slowly changing phenomena. So the question is, how does the potential for atmospheric moisture transport influence floods, and what kind of floods are generated by that, and so forth. So this particular slide that hopefully David's got before you, we did an analysis of the largest floods in the historical record in the gauges in areas which haven't seen human modifications of the landscape significantly, and the smallest floods. And we compared what were the conditions for that season, the entire season, in terms of sea surface temperature, atmospheric pressure, and various other fields. And that's what you're seeing here. And what you see is that you're looking from top to bottom, going up and down the west coast. And what you see is that essentially the sea surface temperature picture for the largest floods to smallest floods are mirror images of each other, in the sense that as the warm pool in the Pacific, equatorial Pacific, moves east and west, the flood potential moves north and south along the west coast. We thought this was interesting. And then, David, could you go to the next one, please? We wanted to build models to see if you could actually predict the annual maximum flood a season ahead using empirical model, which used only 4 predictors of conditions in the Pacific equation: equatorial temperature, and which is surrogate used for that is the Nino 3 climate index, high latitude Pacific behavior, which possibly modulates the storm tracks, and for that we use the Pacific Decadal Oscillation Index, and in both cases we use the mean value of the previous season and the change in the previous season. And we divided our sites into 4 clusters based on the seasonality of the floods, and used the values for the season preceding corresponding to each of those to make the forecast. And to cut through this, what we found was that using the methods that we had developed, we were getting remarkably amazing forecasts of the annual maximum flood, which we have always thought of as a completely random event at most of the sites in these locations. And the degree to which that works is shown in the next slide, which has the box plots with unexplained variance for the season ahead. So David, hopefully you're there.
Yes, so there's out of sample flood forecast examples.
This one, go to the next one, which says unexplained variance.
Explain it, yep.
Okay, so here what we see is box plots across all the different sites of unexplained variance from cross-validated forecasts of the next year's annual maximum flood, and the median there is for the different clusters of sites that we were looking at ranges from about 15% unexplained variance to about 25% unexplained variance, which was unbelievable to me. I still don't believe it today that this is not just an artifact of the statistical thing. Let's go to the next slide, please. This is a year ahead now, and the story is somewhat similar, so we were wondering exactly what's going on here. And we've looked at this quite a bit since then, but let's go on to the next slide, which is called atmospheric moisture transport associated with one of the top 10 floods at different locations. And David, please just keep clicking through these. These are pictures where what we did is that we now went down to the daily time scale, and what the person who did this work did is that they took a variety of stations in across the United States, and for each of the stations, these are stations that are below 1,000 square kilometers in drainage area and above 20,000 square kilometers in drainage area. And the hypothesis was that maybe it is the larger drainages that see large-scale atmospheric moisture transport as causing floods, and maybe that is what is predictable. But the smaller ones, who knows what goes on there. So we looked at these, and what they did is they simply took the calendar dates associated with the top 10 floods in the historical record and went and drew composites of the atmospheric moisture transport, the vector of atmospheric moisture transport over a certain interval in the vertical for each of those. So David, if you're just flipping through these, what you guys should be seeing is as you move along to different places in the United States, that in every one of those places, in the day or so preceding, the moisture is coming from the oceans, bringing a flood to that. And the blue dots that you're seeing are locations of the stations that recorded a top 10 flood on those calendar dates. And what amazed me was that on using this criteria, even the small drainages were getting hit by the same things. And it's interesting because it turns out that if you're experiencing a flood in a large drainage, often most of the small drainages that we recorded were nested within that, so they all experienced the same large-scale atmospheric phenomena. So let's go to the next slide. So this has been interesting because it suggests that slowly varying ocean conditions translate into preferred storm tracks and hence into flood potential. This opens the door for looking at these as phenomena that we could then start looking at the various sorts of adaptation strategies for if we shift our emphasis from watershed-based flood analyses to more comprehensive flood potential analyses, considering atmospheric rivers all the way down into the flood situation. There are two things we need to understand here. One is where is the moisture source? Where does the moisture go once it's evaporated from that moisture source? And second, why does the convergence take place at the location where the flood actually happened? Why didn't it drop the water somewhere along the way? So this is something that we have to work on, but this is not something you're going to get directly out of climate change models or climate models. They are a useful tool to explore this particular. Okay, let's go on to the next slide. And this is my last slide. And the question now is that I want to open this up for discussion with the idea of if our goal is climate change adaptation, what do we think is coming up? What should we be targeting to do? And what are the kind of areas where hydrologists need to push in terms of developing advances? So the first comment that I have is that in my view, climate change should be seen as a major agent of globalization. Today we talk about globalization as something that applies to the economy, that applies to the labor markets, that applies to people in India sitting and taking jobs from the United States, or today they are actually hiring people in the United States to do work in India because it's turning out to be cheaper in some respects. But if you start thinking about it, we are going to have major shifts projected in agricultural potential in certain geographic areas and the type of crops that will be there, and modifications of those crops to suit the new climate that will exist. There are projections for major shifts in vector disease births. And agriculture is obvious, but if you think about vectors like malaria, vector-based diseases like malaria, this is something that requires an analysis of topography and hydrology as they intersect with the climate conditions to determine which specific areas become hotspots as the latitudinal temperature and precipitation belt shifts and which ones do not. Ecological habitats will be modified, so all the species will be migrating as well, including humans. And it's quite conceivable that Canada and Siberia will see massive migrations, and that leads to changes in water demand and so forth. Then the next bullet I have is climate change mitigation. This is the complement of climate change adaptation. This is how do you reduce the potential for climate change, go away from carbon-based fuels, or increase carbon sequestration by a variety of means. If you read that literature, you realize that the vast majority of the things that are being talked about are all potential agents of water stress. And as people think in terms of carbon credits, they are going to induce water stress in areas where they are getting carbon credits in various ways. I'll be happy to discuss this particular story. Last bullet I have under that is that if you think about the story I'm pitching to you overall, for hydrology or hydrologic science itself, our focus will overwhelmingly shift from watershed hydrology, which still requires much research and much to be learned there, to continental to global hydrology. That is multimedia. We are going to have to take on the atmosphere because the type of questions we want to ask are not on the top of the list for the atmospheric scientists. We are going to have to look at multiple scales because the high frequency phenomena depend on the low frequency phenomena. And as you look across the land, which is where the adaptation has to happen, we are very well familiar as hydrologists that it's a multi-scale problem. It's multi-physics because we have to bring together modeling efforts that come from different domains, and we need to seamlessly integrate these physics in an intelligent way. At the moment, I think we are in a very primitive stage with regard to that. So what this takes us to, in my view, is that we are going to be going from atmospheric rivers to infiltration into facetiously subterranean torrents, because we know the scale of water movement below surface, right? But we are also going to bring eco-hydrology into a different frame, which is how does vegetation interact with the generation or degradation of soils and generation of dust, and then the feedback of those into the atmosphere in terms of nucleation potential for moisture. The reason I bring it up is not the same reason that the climate scientists bring it up, usually, which is albedo changes or other similar factors, but because there is a possibility that we will increase atmospheric moisture, but we don't increase precipitation. Depending on the nucleation source, or depending on what is happening with nucleation, we dramatically increase precipitation also. So we need to understand this. And we'll also see radical changes in all the management sectors and adaptation directions. Examples I have here is we've been active in working on restoring the Everglades. I'm not sure what that means in the climate change. It's going to be quite different. Similarly, with the variety of other things I've got listed there. And last bullet in that big section is need for near-term scenarios. Much of the climate change analysis work has focused on generating scenarios that go to the end of the 21st century. From an adaptation perspective, if these people want to engage us, they have to do two things. The first is they have to generate scenarios that are more consistent with going up to 2020, because that's the planning, design, time framework for what most of us are involved in. The second is when you make that statement, it's no longer a free run of a model that is being forced by CO2. You have to get the phasing of the natural modes of climate variability, the decadal oscillations, the interannual oscillations, correct. Otherwise, you're not in the game. This is an effort which is not quite in play, but as people start talking more about adaptation, this is something we have to force that community to work with us on. And that can help define also what we are trying to model. That's my question. Is hydrology really ready to take on such an agenda? It is not everybody's agenda. But since I'm giving this talk, I'm asking that question. And of course, what this leads to is the Obama question, right? Is there hope in climate change for us to make major advances and become rich and famous by having Congress divert large amounts of money to us? That's the end of my pitch. Thanks very much for sticking with me. I know I took the full hour rather than the 40 minutes, so my apologies for that and for rushing through many of these slides. Thanks.
Great, thank you very much. Let's see, we can open up for phone calls right now for questions over the phone.
Thank you, sir. Ladies and gentlemen, if you wish to ask a question, please press star followed by 1 on your touch-tone telephone. If your question has been answered or you wish to withdraw, please press star followed by 2. All questions must be submitted at this time in order for them to be registered. Please press star 1 to proceed.
Thank you, Betsy. Are there any questions on the line? Excuse me, Betsy?
No, sir, not at this time. Pardon the interruption. There is a question from Steve Berg. Please proceed.
Hi, guys. Can you hear me okay?
Yep.
All right. Manu, thank you for an absolutely beautiful scholarly coverage of a complex problem. You're a credit to the profession. Question for you, my good friend, is I'm willing to bet, I sent a note through the web a little while ago, I'm willing to bet 85% of the audience has not studied the Hurst phenomenon. Do you want to tell them a little bit about that and how it gave us guidance for handling long-term kind of things like you're talking about in the Colorado?
Okay. So what Steve's talking about is the idea that when we were, as a community, working on stochastic simulation to generate scenarios that you could score against to better assess the risks associated with particular policies or particular designs of water infrastructure, people started realizing at some time, particularly with an analysis of the Nile River, that simple stochastic models which looked at short memory, like tomorrow depends on today or next year depends on this year, were not adequately describing what was being seen in the data from the longer records that were available, whether from treating proxies or whether from other written records. So there were several different types of stochastic models then proposed, which were capable of generating that sort of variability, and people then generated scenarios in line with those so that you could end up with generating sequences which were dry for a long period and so on, and adapt to them. This is an area that's actually seen renaissance many times in different literatures, because some of these models that generate these long patterns are very simple models fundamentally. The question that comes back is, how do they relate to physics? What is the explanation of this behavior? And what is the nature of some of these things? Specifically by that, what I mean is that you could have patterns that are completely random, that look periodic, or you could have physics which leads to nonlinear oscillations, which if you know some of the key variables, you would be able to predict at least in the short run or so on. Today, when we look at a particular variable like CO2, which is forcing change, this situation gets further muddled because it's difficult to think about how you assign or how do you decide what the actual cause of the trends that you're seeing is. What most people are doing, at least with temperature successfully, is that they are able to show that models that are forced with CO2 give unambiguously different results than models without CO2 with regard to temperature over these longer time scales, and also that if you look at proxies, things are today very different and headed in a singular trajectory. The same on the hydrologic side still doesn't emerge clearly. So I'm not sure if Steve wanted me to say more than that. Steve, perhaps you can elaborate on a particular thing you want to hit.
Am I still on?
Yes, you are.
Okay. No, you did it nicely. The main thing is, Manu, to have our colleagues go and look carefully at that literature, and also what people were concerned about in the 1930s. They were paying huge attention to long-term persistent effects because it really mattered to society. The Dust Bowl years, the building of the dams on the Missouri were designed in that way. That's why they're over-year capacity for lots and lots of issues. There's another part that comes into here, and Jay London colleagues, amongst others, have been looking very carefully at this. And what will matter in Southern California is a term that Harvey Banks introduced in 1953, and the idea is cyclic storage, and they'll be using surface reservoirs and very big aquifers, and possibly recharging in very wet years into such aquifers, and maybe pulling from those aquifers over decades to handle the sort of fluctuations that they run into. So areas where we have large aquifers are going to be used much more because the surface storages are pretty small relative to this. This is a big deal in adaptation. The other part in adaptation comes in is how do people handle brackish water, and there's a big issue there. If you look into the water short area of 400 millimeters a year of rain, parts of Israel, the life cycle costs for desalted water now are coming down to about 47 cents a cubic meter. I pay in Seattle for my regular bill $1 a cubic meter for fresh water that comes out of the river. And these are things that will come into play with energy and other parts as well. So I'm optimistic about all of this simply because I've been aware of long-term persistence for a long, long time. We've been thinking about things to do it. We published in 1982 on what one might do in that sort of thing. It was just mainly an awareness for the community is what I want to share, my good friend.
No, thank you, Steve. I did have the two things you mentioned, which is conjunctive use, essentially, and desalination on the slides I had yesterday before my computer died. And then in the process of regenerating things, I lost that. So I'm very glad that you brought those back up. Early on, I said that the areas of most concern today are in the tropics, and there some of these options become harder to come up with. For example, in India, in the Grain Belt region, and in North China, you have 400 or 500 foot drops in groundwater levels, and there significant effort needs to go into changing the dynamic of both crop choice and irrigation technology. On the solar, on the desalination side, actually the story is going to be, I think, remarkably good. There's work that we are doing here, and I know there are some major groups doing otherwise, where we are looking at solar technologies for not just desalination, but large-scale purification of water. And these, I think, are going to be very dramatically powerful in the sense that the costs are going to be low, and they are going to leapfrog the photovoltaic technologies, because of the simple reason that photovoltaic technologies currently peak out at around 15% efficiency. If you do solar concentrators plus PV, you can get to about 20. Solar to thermal, you can get 85 to 90% energy conversion efficiencies. So if you do a large-scale solar concentrator and the application is heat, you can you're looking at 1,300 watts per square meter coming in, and that's significant in terms of being able to convert energy and then purify water. So I'm glad you brought that up too.
Thanks very much. I'll log out so others can talk.
Dr. Lall, I have a question from the chat. It's from Sony Yasin Gradas. They asked, Dr. Lall, which among the uncertainties involved in the hydrologic modeling impacts of climate change do you feel will be resolved the earliest, and which will be resolved last?
Okay, that's a tough question. The last is sort of easier. The cloud issue remains as the biggest issue, the cloud and convective parameterization issue. A lot of people are working on, but it's truly a tough problem. So I think that's going to take a while to resolve. The issues which are relatively easier to resolve today, I think, are if you look at near-term predictions, seasonal predictions or shorter-term predictions, using statistical methods or even higher resolution climate models to start improving the precision of those sort of models, that is probably one of the earlier things that will happen. Actually, I should say with regard to the last one that's going to get solved, it's probably related to the abrupt climate change issue. Does the thermohaline circulation change dramatically? What are the factors that will cause that? Freshwater inflows in the higher latitudes, the sea ice shelf falling off, those kind of issues are going to be much harder. Also in the tropical belt, things are going to take much longer to sort out, I think. The monsoonal circulations are still not very well represented.
Okay. Betsy, are there any other questions on the phone?
No, sir, not at this time.
I have another statement from Steve Burgess, and he says, soil fertility is one of our greatest concerns. You might enjoy reading a Sankappi Almanac, Aldo Leopold, 1949. Are there any other questions?
We have a question from Steve Berg. Please proceed.
Hey, back again, guys. Sorry, I mistyped. It should have been Aldo Leopold. It's an extraordinary commentary about the removal of native species and how that's affected, amongst other things, soil fertility. And I had the privilege of running a colloquium back in 1990 to provide guidance to the Bureau of Reclamation. It was something run from the Water Science and Technology Board. Our guidance was to give them some things to think about climate variability, and of course the Colorado River was of concern. The late Gilbert White happened to be present, and he, as one of the moderators, and he raised the discussion for people, and he said, we should be thinking about the damage we're doing to soil. It is far more significant than anything to do with climate change. I share that with you just to think about where we fit in the scheme of things, and we've had a relatively recent experience. Manu's comment about the water levels being pulled down in India, that's the benefit of, quote, the green revolution, where people have unconsciously pumped too hard at the groundwater. And the issue in China is trying to go for 2 crops a year when they don't have the sustained water to do that. so we can learn a lot about things that the importation of foods. We fit in a cog in all of this scheme here. But suffice to note, I'm wildly optimistic about the future, and you're listening to a 63-year-old guy. Thanks all very much. And Manu, thank you, thank you, thank you.
Thanks, Steve.
Are there any other comments or questions?
As a quick reminder, if you have a comment or need to ask a question, please press star 1.
Okay, Manu, I have a text message from Steven Speltz, and he says, "Greetings. I have arrived late, so maybe you answered this. I am working in Nebraska, USA, and see increases in precipitation in some of my study areas. Is there a convenient way to determine the natural causation from human-caused effects?"
Wow. Okay, so did I get the cancer I'm likely to get from smoking cigarettes 10 years ago, or, you know, whatever? It's not easy. The first, I would say that in the area that you're in, I'm going to guess that it is in northern central Nebraska on the trajectory towards Devil's Lake, North Dakota. And if you look at longer-term records in your area and the surrounding area, my recollection is that the overall trend over the 20th century is more like a U shape. So if you start looking at only the second half of the 20th century, that's where you see the trend. Having said that, so is it natural variability or human-caused effects? And the human-caused effects could be land use change, irrigation on a large scale, or it could be CO2, a variety of those factors. You'd have to go through step by step on each one to try to understand it. There are people who've done this kind of work. A prominent person of this sort working at the local scale is Roger Pierre-Keys Sr., who's now at the University of Colorado. His argument is that local boundary condition changes can enhance or reduce rainfall, and he demonstrates through modeling how this has happened in the South Florida area and also in India. So you can get insights from models as to what a particular human modification could have done locally, all other things being the same. If you are interested in can you statistically or absolutely distinguish between cause A and cause B, my answer is going to be no. If you want to look at it in the perspective of how do I understand what are the possible ways this could happen and what would be a potential sensitivity of that, then yes.
Okay, Kevin writes back, yes, thank you. It was exactly Roger Pierre-Keys' hypothesis I was thinking of.
Right. Well, I'll add one thing to it. The longer-term variability typically has a larger spatial scale also. So it's like riding a wave. So you're superimposing Roger's hypothesis on top of a position on that wave, and then you have to think about which one is more important.
Okay, Betsy, are there any other questions?
No, sir, not at this time.
All right, I think we're getting close to the bottom of the half hour here, so I'd like to once again thank Dr. Lall for his presentation today. And I think we're going to wrap it up. Just to remind you that on March 14th, we'll be having a presentation by Jim Smith on flooding in the urban environment. And then in April, a presentation on hydro-and-extract community resources for radar rainfall data. Thank you all very much. And again, thank you once more time to Dr. Lall for this presentation, and we're going to wrap it up.
Thanks very much, David.
You're quite welcome.
Thank you for your participation in today's conference. This concludes the presentation, and you may now disconnect and have a wonderful day.